So now let's get back to CFA. Now we're going to talk about some of the fundamental issues and questions that we have to deal with when talking about CFA, evaluating CFA models, and also then setting up our own models and running them. There are three types of model parameters that will become very, very important for us. The first one are so-called fixed parameters. These are parameters where we as researchers predetermine the value and tell R what the specific parameter value should be like. So for example, we could specify that a specific variable loads on a specific factor and that the factor loading should be 1. So this means that R will not estimate this particular parameter, this particular factor loading, but will assume that the factor loading has the value of 1. This is actually something that is very, very important, and I will talk about that shortly because it's essential for model identification within a CFA framework. But we will get to that in just a few seconds. The second type of model parameters, if you can imagine, we have fixed parameters, so we need to have some kind of free parameters. And this is where the value of CFA actually lies, because CFA will allow us to estimate all these different parameters of a factor analysis model. So the factor loadings, variances, covariances. So these are basically the free estimations in a model. And then, of course, we can also constrain parameters. So what that means is, again, they can be, they are similar to free parameters, that they could take any possible value, but they have some kind of restrictions around them. So, for example, we could say, please estimate these factor loadings, but all the factor loadings are set to be equal across populations. So, essentially, we're going to estimate the factor loadings, but we force all the factor loadings to be equal across all the different cultural data sets that we have. This is something that will be very, very important once we start talking about measurement invariance. So to visualize this, I have variable x1, x2, x3 here, and they are caused by a latent variable, and I specified one fixed parameter because x1 is set to 1 here on the latent variable, and then I have lambda 1, which is a free parameter that estimates the factor loading of x2 on lambda 1, and then x3 is specified via lambda 2, so the factor loading of x3 on the latent variable. And we also have measurement errors for each of the observed variables. So, what do we need to do in terms of identifying a model? This is actually something that is not trivial and quite important. Unfortunately, a lot of times people kind of gloss over that a little bit. The reason why it is so important is because if we don't put some kind of constraints around our models, we could find an infinite set of possible solutions, because we have data and we try and fit a model, but since there's no kind of fixed kind of anchor against which we can compare our models, like we could actually come up with an infinite possibility or infinite number of solutions that could all work equally well. So for that reason, we need to identify some kind of parameters, and against this particular parameter, all other parameters are then benchmarked. There are some basic rules. The first rule typically is we need to identify basically some kind of metrics. And the way it is done by default most of the time is we set a marker variable. So in our previous slide we had x1 that was set to have a factor loading of 1. And so this will essentially set the metrics for all the other parameters, because everything will be compared with that factor loading which we set to 1. And so we can always then think of all the other factor loadings. Are they smaller, bigger, how smaller, how much bigger than this particular factor loading that we set to 1? A different option would be to set the variance to 1. This can also be done. There's a number of reasons why some people prefer this option, some other people think it is not so good. For the reasons of measurement invariance testing, people typically use the default option, which is the option with the marker variable. Then another thing that we need in order for our model to be identified is we have to have at least 3 indicators, at least 3 observed variables per latent variable. This can be relaxed somewhat if we have more than 2 latent variables, and these latent variables are freely estimated. We can actually get away with just 2 indicators, as long as these 2 indicators are uncorrelated with each other. So just to recap, we need to set some constraints on our models in order to get them identified. So the first thing that we need to do is we need to have a marker variable that we set, and we have to have at least 3 indicators if we only have 1 latent variable, or if we have 2 or more latent variables, we can actually get away with just 2 indicators. So that's really important. Most of the time, as we will see once we really jump into R, we don't have to do much about this. It is more something we have to keep in mind when we set up our questionnaire. So here's again our example. We have 3 indicators, hooray! We could actually estimate our latent variable, and we set 1 variable as the marker variable. One of the issues that we might come across are so-called just identified models. This is the case when the number of free parameters is exactly equal to the number of known parameters. In this case, we have 0 degrees of freedom, and what it actually means is, what is meant by number of known values is the number of covariances that we have in our data set. So if we have let's say 3 items, we have this little formula here. So we could multiply 3 times 3 plus 1 is 4, so 12 divided by 2, so 6. So if we have 3 items in our data set, we have 6 covariances that we can play around with. So we can potentially estimate up to 6 parameters, and in that case we would have a just identified model. Why does that matter? Again, this will be an issue if we try and estimate lots of different parameters and we don't have as many items in our data set. Then we might run into problems. So again, this is something that we need to keep in mind when setting up our studies, our instruments, because we need to have enough information in order to be able to estimate our models properly. So now let's get to something that actually will bother us a lot, which is namely, how do we know whether our model actually works? Does it fit well? And model fit is one of the key issues within structural equation modeling, and therefore within confirmatory factor analysis, and it's really, really tricky. Because we can estimate any kind of parameter that we want, but an estimated parameter does not actually tell us whether it's actually a good parameter or not, or whether the model fits or not. So we need to know whether the estimations that we got from our data actually represent the data well. And you will find a lot of discussions in the literature, but in the next few slides we're trying to break down this whole complexity and give you a little bit of guidance. Basically, there are a number of different fit categories that we can look at. The first one are so-called exact versus close fit. We will break that down in just a second. And within the close fit categories, we can differentiate between so-called lack of fit indicators or comparative or incremental fit indicators. So let's have a look. The first one, the oldest one, and actually the one that rules them all, is the chi-square. Chi-square basically tests the deviations between what we would expect in terms of covariances based on our model and observed covariances, right? So we have our data, right? So we have all our measured variables, and so we can compute all the covariances between all the individual items. And we also have our model, and based on our model we would expect a certain pattern of covariances, right? So if our model was true, what would be the covariances in an ideal world data set? So these are the kind of expected covariances, and now we compare them with what our data is actually like. And the greater the misfit between this kind of theoretically expected pattern of covariances and the actually observed covariances, the greater this kind of misfit, the larger our chi-square value will be. And so we always try and compare this observed chi-square against some kind of benchmark. And this chi-square value actually will be important for pretty much most of the other fit indices that I will talk about in just a few seconds. The problem is that chi-squares are scale dependent because, as you know and remember from your take-home test, covariances are scale dependent. So they are expressed in terms of the measurement units that we used in our experiment or in our survey. So a high or low chi-square doesn't really mean much. But the thing is, we can actually test against a null model, basically where we allow everything to correlate with everything, so covariances between all sets of variables, and so we can test how much the observed chi-square deviates from basically, like a model where it fits perfectly. And the issue here is, if our chi-square is significant, that is not good news, because basically it means we have some significant misfit in our data. But the issue here with chi-squares are that they're sample size dependent. And here we run into one of those beautiful little paradoxes with confirmatory factor analysis, because typically we want to have something significant, but here we don't want our chi-square to be significant. If you might remember from power analyses, how do you actually get something not significant? You get a smaller sample size. But obviously that's not a good practice as a researcher, because we always want to have a large enough sample to draw some kind of good conclusions, some valid conclusions in terms of our population. So we want to have big data sets. And if we have big data sets that are representative of our sample, we run into the problem that our chi-square most of the time is significant. So what can we do? Should we just throw the chi-square away? There are basically other options that are built on the chi-square value, but try and overcome some of these issues. The first type of so-called close fit indicators are lack of fit indicators, where a smaller value is typically better. And the second type is a comparative or incremental fit index, and here a larger value is better. The specific cutoffs of what is actually good fit or not is really hard to determine, And so a lot of people have run simulation models to find out, like what would be a good fit index or not. And the issue with that, though, is depending on how you simulate your model, so basically how you set up your models, your parameters, etc., different fit indicators will show up as being good or bad. I will use mostly the one simulation model or set of simulation models that was run by Hugh and Bentler in 1999. It's the simulation study that is cited most widely. But we need to remember that there are also problems because, it depends on how you set up your simulation studies. And what they did, for example, they used moderately reliable theoretical models with loadings about 0.7 and then estimated what fit indicators might be good or not and what fit cutoffs might be indicating good model fit or not. So let's have a look. Lack of fit indices. The first one is really the root mean square residual. It kind of works out of the chi-square because it looks at what is left over in terms of the residual correlation after we fit our model. So what is the deviation between our expected correlation between any two variables and the observed correlation? Because it is based on covariances, it is scale dependent. So a lot of people then actually said, let's just standardize that. So it's essentially the same thing as a correlation is to a covariance. So people standardized it. So now it reflects the covariances as correlations. And here Hugh and Bentler argued that if the SRMR, so the standardized root mean square residual, is smaller than 0.08, it would indicate that our model fits reasonably well. A second set of indicators, or a second lack of fit index, is the RMSEA, which is the root mean square error of approximation. So that's quite a mouthful, so that's why a lot of people just say RMSEA. It is similar to the SRMR, so the square root mean residual, the standardized version, but it takes into account the complexity of the model and it does some kind of magic adjustments. You don't need to know the details. What is important here is that this fit indicator is relatively robust. It tends to provide better fit when you have a more parsimonious, so if you have a simpler model, and it's widely used. The people who came up with that particular index are Brown and Kudak, and they were playing around with their data, and they suggested if it's smaller than 0.05, it's kind of, it's basically showing us that the model is fitting well. If it is between 0.05 and 0.08, it fits reasonably well. If it is smaller than 0.1, so between 0.08 and 0.1, it is mediocre fit. And if it is above 0.1, then it's really a poorly fitting model. Hugh and Bentler, in their simulation study, they actually said that we have to be a bit more stringent. So they argued that anything that is smaller than 0.06 would indicate a good model, and anything that is above 0.06 would actually indicate a poorly fitting model. Another interesting feature of the RMSEA is you can actually test for significance and you have confidence intervals. That's something, once we get to playing around with our data, we might look into some of the advantages of having confidence intervals. So these are essentially lack of fit indices. A smaller number means better fit. So now let's go to so-called close fit, comparative or incremental fit indices. The first one, and one that is very often used, is the so-called comparative fit index. It was developed by Bentler, and it uses a fancy so-called non-centrality parameter. The advantage of the CFI is that it may take sample size into account, so it is not as dependent on sample size as the chi-square. The fit index that most people argue indicates a well-fitting model is 0.95 or higher. A second comparative or incremental fit index is the TLI, the Tucker-Lewis index, or sometimes called non-normed fit index. The great advantage of the TLI is that it is not dependent on the numbers, degrees of freedom, so it is not model complexity dependent. And again, a higher value, 0.95 or higher, indicates good fit. The last one that I want to talk about just now is McDonald's Centrality Index, or the MC. The advantage of the MC is that it is not dependent on scale reliability. As you might remember just from a few seconds ago, the simulation by Hugh and Bendler, they used moderately reliable factor models. And so one thing that people have actually pointed out, that if you have very good instruments that have highly reliable indicators, they may show poor fit. And that's kind of paradoxical. Again, you know, the world of CFA is full of beautiful little paradoxes to get your head around. So that's why people have looked at the MC, McDonald's Centrality Index, because it doesn't punish models that have higher reliability. The little problem is very few programs routinely compute McDonald's Centrality Index. You can get it from R, and we will also look into that. And here, cutoffs of 0.9 or higher are indicating good fit. Just quickly, actually, why are they called incremental fit indices? Because they compare the fit against what is called a null model, where you basically have no relationships between any of the variables. And so it always compares how well your fit of your model compares to a model where there are no relationships whatsoever. People have actually discussed that, whether that makes a lot of sense. You can actually really argue about it, but this is how most people these days estimate or test their models. The important thing to remember is there's no single cutoff, there's no single best fit indicator. So what you need to do is you need to look at all your parameter estimates. Remember, a parameter estimate doesn't tell you whether your model fits well or not. But if your parameter estimate is really out of bounds, so we have a scale from 1 to 5 and our parameter estimates are like 200, it tells us something is kind of going wrong here. So look at your parameter estimates, have a check out whether they actually make sense. The second thing is you may want to look at modification indices. So what would happen if we modify our model, if we free up some kind of parameters or we free up some covariances? And it's always a good idea to compare different kind of fit indicators with each other. So look at your chi-square, look at your CFI, look at your TLI, look at your McDonald's Centrality Index, look at your SRMA, look at your RMSEA, and compare them with each other. Do they all show kind of similar patterns, or is there some kind of value that really is out of bounds and is fitting very poorly and others are fitting well? Because each one of them has some kind of advantages and disadvantages. We need to look at all of them together in order to make some kind of good decision of whether we should accept our model as a good fit or not. You can also get more fit indicators, more fit stats, and we might look into that once we play around with our data. So the important thing, the issue that you will potentially lose a bit of sleep over when you start looking at your own data, is how well does your theoretically predicted model actually fit when you compare it with your empirical data. And this is something that we will really look into once we start playing around with our data here. And then the second question that always comes up immediately after we look at our model fit is, what do we do with poorly fitting models? Because The real world is messy, is really messy, and most of the time our model, that beautiful fruit of your countless hours, is not actually going to fit that well. It's my prediction. If it does, hooray, be happy, party, but stay at home. But most of the time it doesn't actually fit well, and so we have to think about what to do. And here again we can look at so-called modification indices, and we will talk about them in the next couple of videos, and then we can decide how we can potentially tweak our model to make it fit better. And here we actually leave the land of confirmatory factor analysis, even though it's called confirmatory factor analysis, because we have these options of modifying our models. We start moving into an exploration of our data again. So we use confirmatory factor models in actually an exploratory way. So what we will start doing in this case is we will start looking at how we can improve the model and the model estimates and the model fit if we make certain changes. So we typically add parameters, so we add, for example, covariances between observed indicators, covariances between latent variables, or we add factor loadings between items and other factors, or we may actually also remove factor loadings. For example, if an item doesn't load on a specific factor, then we might actually remove that factor loading and see whether that improves model fit. So that is it in terms of the theoretical part. And what will happen next is scary. We're going to look at how all of this happens in R. So stick with me and stick with us, and we will get through this together.